Let's do an example of evaluating an estimator and this sort of with a toy population. So these are the kind of typical examples we're going to do in this section. In practice, by the way, these are really good to do to sort of build into your intuition those like fundamental ideas of estimation, statistical estimation. But unfortunately, we're stuck with these little toy examples with these tiny toy populations. Otherwise, the calculations become really ridiculous, right? Because if you imagine to build the sampling distribution, which is what we're going to do here, you have to take all possible samples. And as soon as you have any reasonable size, even if you have like 10 individuals in your population and you take a sample of size 3, you get 1,000 samples, right? 10 times 10 times 10. It's 10 choices for each slot in your sample. And so it's just impossible to do by hand. So we're stuck with these little tiny toy populations. But it's good to do these because people kind of don't see the forest for the trees when they do statistics, because these calculations become sort of not possible to do by hand. In the real examples, so you've got to do some of these toy examples to really get through your head what's happening in the real ones. Cool. So let's consider a population of only 3 individuals. One of them has shoe size 8, one has shoe size 10, and the other has shoe size 10. So there are 3 individuals in the population, but only 2 different shoe sizes because 2 of the individuals have the same shoe size. So let's let theta be the median shoe size in the population. So the population median, parameter theta, it's 10. You look in here, what's the median? It's the value in the middle when you line these all up in order. Oh yeah, it's 10. And consider the sample median as an estimator for this parameter theta. So the notation we have for an estimator is usually we put a hat. So the estimator is a statistic. It's a value you get from a sample that you're using to estimate the parameter that you want to know. Parameter, which is usually an unknown. So in this context, you're pretending that there's this population, but you don't get to see everyone in the population. You only get to see a sample. Oh, and by the way, I should write this down. Determine the sampling distribution of this estimator for samples of size 2. I gotta say that. Okay, good. So the idea is I have 3 people in my population, but I only get to see a sample of size 2. And so from that sample of size 2, I'm going to calculate the sample median, and I'm going to use the sample median in my sample of size 2 to estimate the median in the whole population of 3 people. So let's make the sampling distribution for that estimator, the sample median, and then we'll find the bias, variance, and mean squared error for that estimator for the sample median. Okay, cool. So how do you make a sampling distribution? For samples of size 2, well, you take every possible sample of size 2, you calculate the value of your estimator on every sample, and away you go. So here we go. So if you think about it here, if we let x1 and x2 be random variables that represent the first and second individuals in my sample of 2 people, then let's see what I get here. What could I get? Well, when I take a sample from this population, I think the only possibilities are 8, 8, 8, 10, 10, 8, and 10, 10. That's it. Those are the only possibilities, right? And let's calculate for each the value of my estimator theta hat. So theta hat is the median of my sample. For 2 values, the median is the same as the average. That's the definition of the median. You line up all the values and you take the value in the middle. And if the value in the middle, if you have an even number of values, you just average the 2 closest ones to the middle. So in this case, I'm really just getting the average here of the 2 values. All right. So now I took all the possible samples, here they are, and I calculated the value of the estimator for each one. Now I can, I can write down the sampling distribution for the estimator, right? Yeah. Okay. So here it is. I take all the possible values of the estimator, and I find their probabilities. So now I look through here and I say, what are all the possible values of this estimator? All the possible medians for samples of size 2. Well, 8, 9, and 10. And what are their probabilities? Okay. How did I get a median of 8? I got a median of 8 when both my sample values were 8. And so assuming that I'm taking simple random samples, which I have to do to make the sampling distribution, I have to have a model for the sampling process. We're only going to consider simple random samples in this course. You could have a more complicated model, but that's doing some fancy statistics. Here we're just going to say we're assuming that this really was a simple random sample. So the probability that this 8 happened in my first sample value, well, it really was 1/3, because one of the 3 people in my population had shoe size 8. And the probability of getting 8 in the second spot is also 1/3. And we're assuming that the values are independent. That's also part of the simple random sample definition. So therefore, the probability of getting an 8 in both places, I can multiply the probabilities. 1/3 times 1/3 gives me 1/9. So the probability that my estimator comes out to be 8 is 1 in 9. Now for the 9, the probability of getting a sample with an 8 here and a 10 here, 8 in the first spot, 10 in the second, that's 1/3 times 2/3, right? Because to get a 10 in the second spot, I had a 2 in 3 chance of doing that, because 2 of the people in my population of the 3 had shoe size 10. Similarly here, this is going to be 2/3 times 1/3 to get a 10 in the first spot and an 8 in the second. And using, putting the 2 cases together, this kind of sample happens with probability 2 in 9, 1/3 times 2/3. This kind of sample happens with probability 2 in 9, 2/3 times 1/3. So both cases, I put them together and I get 4 in 9. And finally 10. Then here, right, 2 of the 3 people in the population had shoe size 10, so this happens with probability 2/3. This happens with probability 2/3. I multiply and I get 4/9. So good. Assuming that I have simple random sampling going on, I can calculate these probabilities pretty quick. So there it is. There is my sampling distribution. And if you want to, I should say here, when I say determine the sampling distribution, I should say which way I want you to present it. Here I have it as a table. I could also graph it. Let's make a little picture of it. That's always nice. 8 and 9 and 10. Good, so I have 9, 10. 8, 9, 10. And the probabilities here are going to be 1/9, 4/9, 4/9. So let's make this the 9ths right here. This is up to 4/9. And so my sampling distribution just looks like this. It's the PMF, right? Probability mass function for the random variable theta hat. Great. So on this axis is the probability theta hat equals little x. All right, there it is. So that's part A done. There's my sampling distribution. Part B, find the bias, variance, and mean squared error. So let's find the bias first. Let's actually, right here, maybe we'll find the expected value, and then we'll use that to find the bias. All right, so what's the expected value here? Let's calculate it. This times this, this times this, this times this. You get 8 and 9 plus this times this, 36 and 9 plus this times this, 40 and 9. And it comes out to be 40 and 36, 76, and 8 gives you 84 and 9. Cool. Doesn't look like an 8. All right. Okay. So the average value of our estimator is 84 and 9. So it's not an unbiased estimator. If the sample median was an unbiased estimator of the population median, then this should have worked out to be exactly 10 for any population, in particular for this one. So because it didn't work out to be exactly 10, we know that in general, the sample median is not an unbiased estimator of the population median. In our case, it is this bigger than 10 or smaller than 10? 84 and 9. 10 is 90 and 9, right? Yeah. So this is smaller than 10. So in our case, this estimator, theta hat, the sample median, tends to underestimate the population median. That's not true in general. It's true just because of the population distribution I happen to pick. I'm sure if you took other values here, you could get a situation where it overestimates. But anyway, in this case, with this population, it tends to underestimate the value of the population median, right? The sample median seems to underestimate usually the value of the population median. Okay, cool. And yeah, we'll calculate the bias, and the bias should come out negative because it's underestimating, right? Saying the same thing in two different ways. So let's do that. Let's calculate the bias, variance, and mean squared error. The bias we've pretty much already done. So the bias of our estimator, because the bias is the average value of the estimator minus the actual value of the parameter you're estimating, and we just calculated that was 84 to 9. And the real median shoe size in the population is 10. So when you do that, this is 90 and 9, so I guess you get minus 6 and 9. Something negative, that means that our estimator, like I said, it tends to underestimate. Got something negative. Okay. And next, we're going to do the variance and mean squared error. I'm actually going to do the mean squared error first. You can do them in any order. I would definitely do the bias is the easiest. I do that first. But then I do that first. But then from the mean squared error and the variance, you can always go from get one from the other, which we're going to do using this decomposition of the mean squared error as the squared bias plus the variance. Okay, so where are we now? Right, we're going to take the expected value of the squared difference between the estimator and the parameter it's estimating. All right, so using this distribution, I'm going to look at this. I've got 8, 9, and 10, right? And so the definition, like I was saying, of the mean squared error is the expected value of the squared difference between the estimator and the parameter it's estimating. Now, by the law of the unconscious statistician, the expected value of a function of theta hat I can get by just simply calculating this function for each value of theta hat and multiplying by the probability that theta hat takes that value. So I'm going to start with theta hat equals 8. That's the smallest value, whoops, of theta hat, right? 8 and 9 and 10. So I'm going to fill this in with 8 and 9 and 10. So I've got 8 minus 10. This 10 being the real value of theta, right? The parameter I'm estimating, the median shoe size in the population, times 1 and 9, so the probability of getting the 8 was 1 and 9, plus, next is 9 minus 10 squared times 4 and 9, because the probability that theta hat comes out to 9 is 4 and 9, plus 10 minus 10 squared times 4 and 9. Just confirming those are the right probabilities. That's what I remember, yeah? 1 and 9, 4 and 9, 4 and 9. Yeah, for 8, 9, and 10. Okay, and so I just do this big calculation. This is negative 2 squared, which is 4. This is negative 1 squared, which is 1. And this is 0 squared, which is 0. Okay. And so all in all, I end up with 4 ninths plus 4 ninths. 8 ninths, pretty close to 1. Great. And then finally, I got to do the variance. So I'm going to use this, sometimes called the bias variance decomposition of the mean squared error. So it's the bias squared plus the variance. Okay. And so if I know any two of these, I can figure out the other one. So the mean squared error was 8 and 9. the bias was minus 6 and 9, and I'm going to square that, and that should let me solve for the variance. So I have 8 and 9 here, 6 squares 36 and 81 plus, I should have reduced that, eh? Oh well, too late now. Plus the variance. Okay, and now, oh no, okay, this is fine. Right, so 36 and 81, these are both divisible by 9, right? 36 divided by 9 is 4, and 81 divided by 9 is 9. Nice. Okay, and then move that over there, and I'll just end up with 4 and 9, right? 8 and 9 minus 4 and 9 gives me another 4 and 9. Variance of theta half. Great, fantastic. So, recap. If you're using, in this particular case, you got this population with 3 individuals, and we're using a sample of 2 individuals, using the median of that smaller sample to estimate the median in this whole population. If you do that, what happens? You get a sampling distribution for your estimator that looks like this. Your estimator systematically underestimates the value of the parameter you're trying to estimate, 10. Right, which you saw here. It underestimates it by minus 6 over 9. And the average squared error of your estimate is 8 over 9, around 1, and the variance is 4 over 9. Cool. And by the way, this this variance, just to remind you, this variance, it really is the variance, right? Sorry, this variance here, it really is the variance of this distribution, right? This distribution has a mean and it has a variance. That's its mean, its expected value, and its variance we found to be, 4 and 9.